Hey guys, my name is Adrienne and welcome to Organic Chemistry 2, Part 12 of these recorded sessions. Today we'll be going over for most of y'all Chapter 24, aka the last chapter, in general carbonyl condensation reactions. So, again, this is our last session, so without further ado, let's get started. Y'all know what to do, right? Okay, so y'all know what to do as well. Pause, screenshot, answer, do what you will, scroll forward for the answers, things like that. So, and if you're sticking around, let's get started. So, one, what is the general name for the reaction formed in an aldol addition reaction? This one, pretty simple, and you guys should have gone for this one, B, beta hydroxycarbonyl compound. So, aldol addition, pretty much two aldol groups, aldehydes, reacting with each other and then creating the product, and that product is the hydroxycarbonyl, right? So just to kind of visualize it, right? And with this, an alpha carbon bonds to the beta, um, to the carbonyl carbon, I should say. So let's use this carbonyl carbon to bond with this alpha carbon, right? So C alpha to make that new bond. And with that new bond, right, pretty much going like this O will turn to an OH. So giving us a product, alpha, beta, hydroxycarbonyl compound. So beta hydroxy and then the carbonyl, right, compound. So B. So nothing too crazy. And I like this chapter because pretty much everything is reacting with itself. So that's good. So you don't have to worry about all these other crazy things, and you just have to worry about, oh, it's gonna react with itself, so I don't gotta worry about the reagents, right? Like what we've done before a lot of times, so that's good. And two, which of the following statements about aldol reactions with either aldehydes or ketones is true? So this one, you guys should have gone A, right? And kind of this should make sense, um, considering what we learned last chapter. So we know ketone is preferred, right, in equilibrium, preferred than aldehyde. So A is basically saying if you have an aldehyde, it's going to go to ketone. If you have a ketone, it's going to stay with the ketone. So that's what A is saying. So, and this is equilibrium, right? So it makes sense that equilibrium favors the products with the aldehydes because it's going to go to a ketone, and the equilibrium favors starting materials if you're a ketone because you're a ketone, right? Three, what is the aldol product from the reaction following compound with itself, right? So a lot of these is reacting with itself. So let's do that. So this is pretty much like this, right? And then plus itself, pretty much, right? So again, we're gonna go with the the carbonyl carbon to the alpha carbon, right? So let's say this is the carbonyl carbon we're choosing, and let's choose this alpha carbon over here, and they're gonna bond somehow, right? So which one of these is that um, possible product? So this one, you guys need to do like a little bit of visualizing, right? This one, you guys should have gone B, right? And this you kind of have to twist it because you see how in B, let's redraw B. This is our OH, right? And this is our new bond, the new bond we made, and this was just turned twisted up, right? So nothing too crazy, so kind of visualize that. But other than that, I mean, there's not really, it's not complicated visual wise, it's not like the RNS or like the 3D or the shared conformations, right? So this is just twisting and then twisting again. We know single bonds can twist, so no problem with that. 4, what is the alkyl product of acetone? So again, acetone plus acetone, right? And again, with these questions, right now we're working with structures, right? But they can also do it in name form. So acetone with acetone, and then they could have you answer what the name of the product is, things like that. And we've seen a lot of that before, so you guys shouldn't be surprised. A lot of different questions with reactions and things like that. So again, as always, let's do this carbonyl carbon with this alpha carbon, right? So let's see, and let's twist it up, and let's do this, right? OH, right? So something like that. Let's see, does any of that match what we have? Um, yes, which is this one's 2, or I mean 1, right? 1, and you can kind of also tell some of these are not acetic acetones, right? 2 and 4, they have like propio, right? So you can even ask um, if these are propio propiones, right, or something like that. What would the product be? So in that case, 4 would have been 1, right? A good one, things like that. So this one was, what did we say? A, right? A. So not too bad, nothing too crazy. Again, this chapter is easy, especially for your last chapter, and I'm pretty sure. I don't know if this is gonna be its own test for y'all. I'm pretty sure it's gonna be on the final. You know what I mean? So not too bad, right? Okay. So let's get to a new page. So pause, do your thing, and stick around if you wanna hear the explanations. Okay. So 5 following carbonyl compounds do not undergo when treated with aqueous sodium hydroxide. So aldol addition, right? Aldol addition. What are the steps? So first we have enolate, right? We form the enolate, and we know what enolates are. It's pretty much just an anion on the adjacent carbon where the double bond is, right? And then 2, we have the nucleophilic addition, right? Pretty much we're combining them, and then protonation, 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 which will get the OH part of it, right? So which one of these can't undergo any of these 3? You guys should have gone A, because in A, and this is even a better visual, so A, where are we going to inolate? Nowhere, right? This alpha carbon here um, is full, right? There's already 4 bonds to it, 1, 2, and there's a double bond, 3, and then 4. So there's no enolate. So how are we going to proceed with the reaction if we can't even do the first step, right? So, and then the rest of them can hold the enolate. Um, for 2, it's not an aromatic, so it can go in that ring, so it's fine. For 3, it can go to the methyl group on the side. For 4, same thing on the methyl group on the side, right? 6, which is an unsaturated carbonyl compound formed in the dehydration of the following. This one, you guys should have gone A, and this is one of those, there's not really, it doesn't follow a specific reaction. It's just one of those things that, do you know what dehydration means, right? And in this case, we know dehydration, obviously, pretty much water, right? Taking out the water. So obviously this is our OH, and now we have to look for our other H. So either here, one of these, one of these, or one of these, right? So which H is going to be eliminated? So in this case, it's going to be one of these because, again, going back to alkenes, we want the more stable it is, the more substituted it is, right? So this, if the double bond was here, there would be three branches, right? Compared to two, there's only two branches coming off. So that's why we chose one. So let me redraw that. So, right? So it's not really specific to one of the. This is just relevant to this chapter because we do work with dehydration a little bit towards the end. So that's why they kind of mentioned it, kind of like, okay, you know what dehydration means. Testing you, right? Reviewing you, which is good. 7. What is the name given to an aldol reaction between two different carbonyl compounds? This one is just a given. We have a regular aldol, we have cross or mixed aldol. So this one you should have gotten B, and this is just a purely terminology question. So which is always good because they're gimmies, right? 3 points. So we said crossed or mixed, and you'll see cross mixed reactions for the other types of reactions we'll go over later as well, right? 8. In what situation can the yield of single crossed aldol product be increased? And actually, in number 8, it tells you cross aldol. So 7 is definitely B, right? Okay. In what situation can be increased? This one, you should have gone A for the pure, pure fact of just saying the electrophilic carbonyl compound is relatively unhindered and is used in excess. Unhindered, excess, good signs for a reaction, right? B is saying hindered and limited amount. Total opposite. Obviously, we know hindered um, reactions are going to be way, the rate is going to be way slower and in a limited amount. I mean, obviously. C, the nucleophilic carbonyl component. So, are carbonyl components nucleophilic or electrophilic, right? Is unhindered. The nucleophilic carbon. So pretty much the same questions, and we know for sure carbonyl components are electrophilic. So C and D are automatically off, right? So that's what we chose A. And for that, you don't even need to kind of know anything about the reactions, kind of just from past questions, past chapters, past experiences with reactions, right? We know unhindered is the best, and especially in excess, right? It's going to increase your product. Okay, so not too bad, right? Last chapter is being good to us, which is what we need. I mean, it's towards the end of the semester. We need a little, cool time, so it's always good. Okay, new page, same, same rules. What you guys got? 9. What cyclic product is formed in intramolecular aldol condensation when following compound is treated with aqueous NaOH? So this one, obviously we're going to make a cyclic of some sort, right? But what type, right? So again, what is this? How many is this? That many? I think. Okay. So same thing, same concept, carbonyl carbon with an alpha carbon. So let's do this carbonyl carbon with an alpha carbon, right? And this one is a tricky one because where do you, which alpha, this one or this one, right? So in this case, you guys should have chose A, right? And so that means the alpha would have been here, right? So make a bond right there, right? And basically you're closing it off. And if we have chosen the other, let's see, if we have chosen the other alpha carbon, let's say this one, if we made a bond right there, what would have been our product? So we have 1, 2, 3, 4, 5, right? So we would have had something like this. We would have had D, actually, right? So something like this, right? So with this, why did we choose the outer one versus the inside one? Well, in this case, well, actually, for 1, 2, and 3, those are just counting the carbons, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. C has 10, right? Both 1 and 2 have 9, but we know on the carbonyl, right, where that ethyl group is and the methyl group is, kind of just have you have to kind of number your carbons, okay? And here it's always gonna be four, oh, 4, 5, 6 membered rings, right? And we chose the 6 membered is because again it's more stable. We know the angle for the stability is what 109.5, and cyclohexanes have that, right? So this is more strained, but this would be possible still. So and this was the A, and this was D, right? Okay, 10. What reaction type is Kleisen? So again, one of those questions that you just have to know. And this one is a what? So for 10, you guys should have gotten D, nucleophilic substitution. And again, for Kleisen, we know two esters, right, make beta ketoester, right? And they substitute one of those esters for that keto group. 11. This page has a lot of questions, I feel like. Yeah. Okay. 11. Following Kleisen reaction, we just talked about that, right? So we have, let's draw two esters. Plus, I feel like doing them on top of each other will show the reaction better. So again, we're substituting one of these, right, for, well, I guess on top of each other wasn't a good idea because now I have to do this for this, right? Well, actually, yeah. And you guys should have gone what? What product did you guys get? 11. You guys should have gone something like, let's see, something like D. And again, so another thing here is that we know it's going to make beta keto ester, right? So which one of these are beta keto ester? In this case, 11. Oh, actually, it's C. Sorry about that. Beta keto ester. Um, we have the beta carboxyl group and then the ester group, right? And for one, it's missing that methyl group, so right, and then oh, right, so this is where they bonded a new bond, I should say, right? So And then 3 is not beta anymore because it's in the delta, right? It has one extra carbon in the middle. Sorry, sorry. C, beta ketoester, right? Ketoester, and you'll see later, um, you'll see something that actually is the next question. Okay, so 12. What is the general product cross glycine between ketone and ester? This one you guys should have gotten D, and you guys might be wondering, why is it not a beta keto ester? We just talked about beta keto esters for the last two questions, right? Well, in this case, this is what? Between a ketone and an ester, not two esters, right? So, and you end up with this, right? Because this part is the one that gets substituted, right? So, pay attention to that. 13, and since they said glycine still, so it's still a substitution, right? A nucleophilic substitution, so we had to sub this out. 13, what is the intramolecular glycine called? So again, um, what's it called? More terminology. You guys should have gone Diekman, right? 14, in microreaction, where does the nucleophile attack? The the alpha beta unsaturated carbonyl component. Obviously the beta carbon, so B, right? And this one, we know for sure in a micro reaction that we need an alpha beta unsaturated carbonyl, right? So pretty much alpha beta unsaturated. So something like this, right? And alpha beta, and this is where it attacks the beta side, right? Okay. Oh, that's it for 14. Okay. Now let's go on to the next page. Okay. Pause the video, do your thing, answer the question, see what you guys got. 15. What are the starting materials for Robinson annulation? So this one, you guys should have gone AAV unsaturated compound, and then enolate. So what makes this different from the rest of them? Well, the rest of them, they don't have unsaturated, right? They don't have that double bond. They just have carbonyl groups. Um, B would have two carbonyl groups and an ester, or an extra oxygen, right? C and D, they have dicarbonyls again, but we want that double bond, which is unsaturated. 16. The following reaction is an example of what type of reaction. This one, what do you guys get? What's going on here, right? So you guys should have gone here, D, because you make a cyclic, right? Cyclic from ester. And we know Diekman is the intermolecular glycine, right? Which deals with esters, right? And what about Robinson? Robinson also makes esters. I mean, not esters, cyclics. But in this case, Robinson needs what? We just answered it on number 15, right? It needs AB unsaturated, carbonyl with enolate, right? So we don't have an alpha beta unsaturated carbonyl in this reaction, so that's why it wasn't Robinson. 17, the beta hydroxycarbonyl product of an aldol is oftentimes not isolated. Why? It undergoes elimination, possible, like true, right? That's true. Elimination. The hydroxy group is oxidized, so carbonyl Um, fair, right? Question mark. The hydroxy group reacts with the carbonyl to form a ketal. That's false, right? And again, let's do our aldol reaction. We have here enolate formation. What's our two? Nucleophilic addition. Three, protonation, right? So in this one, it's not isolated. So our reaction, this is what they're talking about, the reaction. So and we have two equivalent, right? Two equivalent. And you end up with this OH, right? And this is the intermediate they're talking about. So this is in the product, and the product is this, right? So why is this um not isolated? Well, that's because you guys should have gotten this one as D because it's eliminated via enolate intermediate, right? So the elimination this has is elimination of conjugate base, right? And that's important because that conjugate is what the enolate is. So I guess I should put that here. But it's not A because it's not we're not eliminating the water in a sense. We're eliminating the hydroxide, right? And water is not a good leaving group, right? It's just very neutral, and it's not a better answer than D, I guess is what I'm trying to say, right? And the hydroxy group is not oxidized, it's eliminated, right? So the hydroxy group is eliminated, it's not oxidized. The hydroxy group C, it says reacts with carbonyl. It doesn't react with carbonyl to form a ketol, right? It just gets eliminated, right? So that's why it's D. Okay, 18. Would this cross-aldol reaction work well? Why or why not? So in this one, you guys should have gone. Let's see here. A. Yes, the diketone is significantly more acidic, so this enzyme can be formed selectively. So last chapter we talked about all the dicarbonyls, right, and the acidity, things like that, and we know for sure that this hydrogen is acidic, right, and that this is where the enolate will be formed, right? So this can just attach itself when that enolate is formed, right? But without the oxygen. So that's why um, they can be selective like that. That's why it attaches where it attaches because that's where the enolate is most likely to be. And let's look at the other answer choices. Yes, the aldehyde is significantly more acidic, which is false. Right out false, right? The diketone is more acidic than the aldehyde, so that's false. The aldehyde is significantly more acidic. Again, false again. So B and C completely false because the aldehyde is not more acidic. So D, this NA cannot be formed um, selectively. We do know the diketone is more acidic, but because it's acidic, we know that H can be taken out to form an enolate. So um, enolate can be formed, right? So that's kind of how you go about that. So let's go to the last page. So again, last time you're pausing, right? So let's get this started. Okay, 19. Complete the statement. A major difference between the aldol condensation and the glycine condensation reaction is that A, the aldol reaction involves substitution with a glycine involves addition. B, aldol is acid catalyzed, while glycine is base catalyzed. C, base catalyzed, requiring full base. D, aldol is base, while glycine is acid catalyzed. So this one you guys should have gotten C because the aldol reaction is base catalyzed, right? So B is off. Um, let's see. Yeah, while the Claisen reactions full base. We are at equivalent full base. Um, and also for this one, the, for A, the aldol reaction involves addition, right? It's nucleophilic addition, right? While the Claisen involves substitution, the esters substitute. So A is opposite. Um, D, again, Claisen is base catalyzed, right? So both aldol and Claisen are base catalyzed. So those are just like little infos um, that you just need to pay attention to, right? And just knowing what the reaction does is enough, right? 20. There are several variations of the aldol reaction. Which of the following types of reactants leads to the only one possible product with aldol condensation? So this one, um, two different aldehydes with alpha hydrogens, two different ketones. Any aldehyde can react to form a pair of reactants where one reactant has no blah blah blah. Okay. So this one you guys should have gotten D because we know if only one reactant has the alpha hydrogen, obviously that's where the enolate is going to form, right? And that's what D is saying. So A is saying if there's multiple alpha hydrogens, if there's multiple alpha hydrogens, then you have multiple places um, to form a product. So that's not good. And we just want one product. And again, with B, right? It has multiple alpha hydrogens, so obviously that enolate is going to form wherever, right? So that's not going to form it. Um, that's not going to form one product. Um, and C is just saying like any aldehyde or ketone. So that's not very specific, or it's not again that enolate can form anywhere, right? So that's why it's D, because if only one reactant has an alpha hydrogen, then that's where it's going to go for sure, right? Like that question, the acidic proton that we just looked at, that's where that enolate is most likely to go, right? Even though that has multiple ones, the most acidic hydrogen is the one that's going to pop off and turn into an enolate, right? Okay. So that was pretty quick, and I think it's because we skipped the intro part because you guys already know, right? So let's go ahead and do the summary. Our last summary, right? Okay. So first things first, let's start with um, condensation reactions, right? So first things first, enolates, enols can react with other carbonyls, right? Which is pretty much the point of this whole chapter. One nucleophile and one electrophile, which is pretty much again the reaction, the condensation reaction, um, will make new bonds with the alpha, and I'm going to put C, carbonyl carbon um, bond, right? New alpha carbonyl carbon bond. So now let's go to this, right? The aldol reaction. And this one has multiple parts, so I should have done it in a new page, but it's okay. So basically, two equivalent, right, of aldehydes, OH minus, H2O, and you form this. alpha beta, and then this is a new bond, right over here. So what's the steps? Again, we form the enolate, nucleophilic addition, which is pretty much the other aldehyde, right? And 3 protonation to make that OH nation. And now we talked about, and this can be either again aldehyde or ketone, right? Um, with base, right? Aldehyde ketone with base, which is the H2O, which is the OH part. So now we said this isn't usually what's it called, isolated, because something happens to it, right? So that's what we call, and actually I'm just gonna put this aldol reaction. I'm just gonna name it this way because it's gonna be like a sub heading of the aldol reaction. So pretty much it's reversible depending on the beta carbon and carbonyl, right? So that's why we have this aldehydes favor products, and then ketones favor reactants. So that's the whole equilibrium part, right? So no big deal. We know why, because ketones are gonna be the most um, favorable, the more stable. It has the C. Um, it's the more stable, right? And that's going back into the last chapter with the enol, with the keto enol tautomerization, right? And now we have this, the aldol condensation, and this is where we said that it's not always isolated, right? Initial aldol product not often isolated, right? So let's try that again to equivalent, and hopefully you have room, right? OH minus H2O. So basically, it gets dehydrated, right? So we have, this is our aldol, and then this is our dehydration part, dehydration. And that's because through elimination conjugate base, right? The carbon ion and the product, right? And also when further conjugated. So this happens when it's more it gets conjugated and um, conjugated, right? So nothing too crazy, and it's spontaneous, um, and with the elimination of the OH and the H over here, right? So there, leaving, right? And that's it pretty much. And again, you can go backwards, forwards, retrosynthesis, right? So nothing new. Just know that aldehyde condensation is a thing as well, right? So now let's go to the crossed mixed aldol reaction. So this is when two different carbonyl compounds compounds, right? Not useful when, and this is where we left off with the last question, right? Not useful when multiple alpha hydrogens. So the uses: one alpha hydrogen equals one product, right? And acidic hydrogen or alpha hydrogen um, anilate. So that's the one that's going to anilate, which is what I think number 18 was, right? With the acidic hydrogen forming things like that. And let's see. I think we'll stop here for this one. Cross mix, right? And again, this is still the same kind of reaction, alpha to carbonyl carbon, whatever, right? Now let's go to intramolecular reaction. Aldol. So this one, for 5, 6 membered rings, um, right? So obviously for this one, like cyclopentane, cyclohexane, right? And then we have our last one, directed reactions. So directed reactions is kind of what the last question was, but that last question was just asking for one product. So obviously, if it has one alpha hydrogen, that's where it's gonna go, no matter what. But this one, it's gonna be anilate, um, by LDA, okay, and then 2 electrophile addition, right? So pretty much, if you have an LDA and electrophile, you know it's gonna be directed, and it's not really like a good direction because we know LDA is super strong, so it's gonna end up um, pretty much reducing everything, right? So, but this is extra information again, right? Okay, now let's go to the good part, the Claisen reaction, and then we'll have a couple more reactions, right? So oh, two esters. I don't know what that was about. Two esters in presence of alkoxide base. Of alkoxide base, right? So then forms beta keto ester, but not always, right? And this is only with two esters. So something like this, and let me write small because again, two equivalent, right? NaOET H3O. Okay. Oh, this is an ethyl group, so there. Okay. Um, now what are the steps? We have enolate. So enolate is pretty much going to be always the first one. 2 nucleophilic addition. 3 leaving group leaves, right? Leaves. 4 protonation. And then 5 deprotonation. Deprotonation. So a little bit, I mean, obviously there's more, it's more than the aldol reaction, right? And now we have the crossed or mixed, right, glycine. So this one happens when only one has alpha hydrogen, right? When it only has one alpha hydrogen, that's one product. So you're kind of sensing a pattern here, right? I mean, if you only have one alpha hydrogen, that's all where the product is going to be. Um, Anolate always formed on ketone, right? So that's a good one. Don't forget that on ketone. We kind of did a question on that earlier as well when it was mixed. When we got the beta, like carbonyl instead of the beta keto ester, right? Um, and reacts best with esters that have no alpha hydrogen, right? So pretty much cross mix happens when there's only one alpha hydrogen and that's on the ketone, right? So nothing too crazy. So lots of good notes. Let's go to Diekman. And I like these reactions because they're all named, right? So it's like it's good, and you've got a lot of questions on that terminology, right? Which one is Diekman? What does it do? Which one's Robinson? Which one's Glycine? Blah blah blah. So that's good. So this one, pretty much intramolecular glycine, right? And this one makes 1,6-diesters or 1,7-diesters. These are 5 rings, 5-membered. So like cyclopentanes, things like that, 6-membered. So remember these, right? And again, first step, anilate. Second step, nucleophilic attack. Third, leaving group leaves. Fourth, protonation. So pretty much exactly the same as the glycine, right? 5-deprotonation. So the only difference is it's in, let's see, it's inside both of it, right? So there you go. Now let's go to Michael. Michael reaction. 2 components are needed, right? We need the enolate and we need the what? Alpha beta unsaturated carbonyl. Carbonyl, right? That's what we need. And this one, we have the enolate, nucleophilic attack, but this time on beta carbon. On beta carbon. So that's a special one, right? 3, this on protonation. So this involves 1,4 addition, right, of resonance stabilized and late to the beta carbon of the alpha beta unsaturated compound, right? So that's why it does that because of the resonance stabilization, right? Which makes sense. Can't blame it. Okay. And then now, last but not least, the Robinson annulation. So this we're gonna make a ring formation, right? So an attached ring, things like that. And this is pretty much a combination of Michael plus intramolecular aldol reactions, right? So it's a mixture of that. And first, we have, since it's a combination of the both, we'll have our alpha beta unsaturated, right? And then we'll have the enolate. And this could be any enolate, of course, but this was what we're using, enolate. And this is where the reaction takes place. Again, the beta carbon, right? The beta carbon is the one we want. And it goes to the alpha carbon, right? And these alpha carbon of this unsaturated to the carbonyl carbon, right? So that's what's going on. That's where the ring is happening. So nothing too crazy. And this kind of reminds me of the Dill's alder, right? Good times. I think that was what, OChem1? So base OH minus with H2O, or we can use OET, so an alkoxide. And we're forming, and these are the new bonds, right here, right? And there's a double bond here from that carbonyl. So, okay. So what happened here? Pretty much place alpha carbon of enolate next to beta carbon on unsaturated carbonyl, which is what we did, and two join carbons together, right? So this one makes three new bonds, um, or actually here, these are actually two new bonds right there. So we have one new, or two new sigma and one pi, which is what we have, right? And the product, oh, it's green. The product is going to be 2-cyclohexanone. Hexanone, right? Which is what this is. So, nothing too crazy. And again, with this, same with the beta keto ester, things like that, this is what you're going to be looking for as a product for Robinson annulation. So, with that being said, that's all I have for you guys. Last session, right? So it was cool. It was whatever, right? We're done. Good luck. Um, on your ventures afterwards. Um, and again, I guess I can't see you next time, but you know, have a good rest of your undergraduate careers. I don't know. Thank you guys for watching, and hopefully you guys learned something. Hopefully you enjoyed it, and yeah, good luck. Bye.